Today, we are still covering the control problem that we had done with approximation. And previously, we had looked at just the same sort of techniques we had used before, like variations of Sarsa and these gradient versions of Sarsa that update the parameters of some approximation function. And we had gone through the mountain car example and showed a number of some unsuccessful and successful solutions. But in general, the solution looked something like this, where the value function, you can sort of follow the increase in value function in the same phase space. As here I'm plotting the trajectory of the car. And this is showing the position of the car over time, where the goal is to get to the this value of 0.5 on the right side. I'm not really going to go through the example again, but the idea is the car is in this trough and it has to oscillate back and forth a little bit to build up enough momentum to get here. And the goal is to learn the policy that does that. So this was one solution method that was showing that sort of converted it to a tabular problem and solved it in one way. But then the methods that are used in the book, like this is using the tile coding approximation, and it still finds a pretty good solution, but this is now stochastic and there's noise, sampling noise in the process. So the point is that the technique will find some solution which, like, this solution works even though the value function and the policy don't look much like what is probably close to what the optimal policy is here. But the actual reward value ends up not being that different. So it ends up not mattering so much for the solution. But these techniques were all using the same style of temporal difference learning we had before, trying to maximize the discounted future reward. And you can develop all these different Sarsa techniques. You can use linear and nonlinear approximation techniques. So we had been through all that. And then the next part of this chapter introduces the average reward setting, which is a pretty different, well, yeah, it's different under certain conditions than the discounted reward setting. So to sort of look at this in using a more familiar example, I had gone back to this grid world that we had used in part 1 of the book, and I'll come back to this, but I had done a number of things to display like what is actually happening in the average reward setting. But when you define this here, so I'm going to use this a little bit to see if it's easier to make sense of what's happening here. But this quantity here is the definition of the average reward. And oh, sorry, there should be a 1 over h here. So what this is doing is, assuming there is some expected value of the reward at a time, and here, like, this is the definition in expectation, but here you could imagine like having some reward sequence, from 1 to h. And then if you sum these values up and divide by h, that is what we're defining as the average reward, which is different from, recall what we had before was we would take R1 plus gamma R2 plus gamma squared R3, and that was what this was like previously G for the discounted return. And now we're considering this, other hypothetical quantity, which we could also try to sample. The way you would sample it is you would observe some reward sequence out, and the more samples you collect over time, you're eventually approximating this. So, this, you can always have this like finite sum out to some point, and then divide by h, and this is just going to be like the mean value of this. So one idea that's presented in the chapter is, for a given policy, maybe like this value exists and it's something that we could calculate. And then the goal would be to find policies that have the highest value of this, where now like this is actually a single number. So, before we had, had the value function like at a given state under a policy, and that was equal to the expected value of g of t for what we had before, where g of t was a discounted return. Of course, I'm leaving out here the fact that s of t is equal to s, but this had a separate value at every state s, and the goal was to find some value function and associated policy where these values exceeded the value at every state. But now in the average reward setting, it seems like there's this single number r, and so then the question becomes, what types of problems, for what types of problems does this r actually exist? So it should be like what isn't that, I mean, I guess there's cases where it might be a problem, but we can always take some observed reward sequence out to, a point and compute this limit. And this limit in most all cases we look at will exist. But then in order to develop the algorithms that actually optimize this and try to find a policy that produces a higher average reward, you have to develop these other expressions. So like the next expression looks almost the same as the first one, but you can see that now the h is gone. So now instead of this being an average, we're saying, well, maybe the reward sequence, if you look in the limit of infinite time, just has some expected value, which we could calculate. And if you look at some reward sequence that goes out like here, like a very long distance, now these reward values that appear are going to depend on what we had defined before, that is the distribution. Like so this was like the probability of like being in state S at a given time. And that, this value, if it exists, shouldn't actually depend on what time we're looking at, and then in which case this would be the steady state distribution of states. So we can look at the whole state space, and under some policy, yeah, this should be a pi too. So, under some policy, we might expect the states to appear with some, well-defined probabilities that we could calculate, and then there would be some associated reward sequence that we could also calculate an expected value of. So if this exists, like let's say that this limit does exist, then if you look at this sum that we had previously and you look out to infinite time, all of these terms, because of like the definition of what the expected value is, that previous limit, like all of the terms in here, we could just replace them with whatever this expected value is. And then we don't have to take the average anymore. And we can just look at the long time limit of this. But that is assuming what I just said, which is that this limit actually exists. Now, there is a problem with this. Like, for example, and this will come up in one of the exercises, where if you have a reward sequence that's like 1, 0, 0, 1, 0, 0, 1, 0, 0, and you have some policy where this is produced, and then this is like t equals 1, 2, 3, 4, right? So now, what is the expected value? Yeah, I already have the pi here. So then like, what is the expected value, like this expected value, if we have some reward sequence like this? Well, we could just replace this expected value by actually like a definite number, because if the sequence really repeats like this, then the expected value actually depends on t, and it's just this sequence of numbers. And it's not independent of t anymore. And you can see that as you go out to further and further t, we're going to get either a 1 or a 0, depending on what the t is. So this limit actually just doesn't exist at all. So that's one of the problems if you have some repeating reward sequence. The other problem that could happen, because
Well,
um,
so to
mhm,
be clear though, like the line 1, 10.6 exists in this
yeah,
case, but not 10.7.
yeah, exactly. So in this case, like r of pi is 1/3,
Right.
because you could see if you actually compute the average, you're going to get 1/3. And in this case, the fact that if we cut it off at like here, it's going to be slightly more than 1/3. But as you take this out to infinity, those minor differences, like that error term goes to 0. Whereas if you do what is done in 10.7, where we just replace this average with this quantity, now we might have a situation where the limit doesn't exist. So now the statement that the book makes, so yeah, so there's another problem here, which is that we could, let's say, actually have a case where the expected value of RT, and we have this limit as t goes to infinity, like this could equal some value, but the value could, like, so this could be like given that s sub 0 is equal to s. Now this value could end up depending on s, um and that would be a problem, because then the average reward, which we're trying to have a single number for, we don't really have a single value for this, because there could be a case where, like, if we had picked some s naught that was different, then we'd end up with a completely different average. Like, there's not a specific, I don't have a specific example of that, but you could imagine, like, maybe there's a problem where if you start in one state, you do end up, I mean, if you ended up with this kind of reward sequence, there you'd already have a problem, because then the limit doesn't exist. But let's say that you don't have this reward sequence. Like, let's say you actually have a reward sequence where, like, the expected value of RT is equal to 1/3 in the limit, and like this expected value actually does exist, and it's not this alternating sequence. Like, maybe like this is actually, there's a random probability of getting, like, a 1/3 probability of getting a reward of 1 and a 2/3 probability of getting a reward of 0. So that would be that case. But maybe like this is true given s naught is equal to like s whatever, and then maybe this is like a quarter if s naught is equal to s prime, and then this would also violate the assumption in this problem. And if this was the case, it's likely that the problem, you'd have a situation where this on policy distribution doesn't exist either, or that it depends on the starting state. So this final statement here relies, like all of these things must be true. So we can't have a repeating reward sequence. Um, Even if we have this expected value existing, it can't depend on S naught. And then ultimately, this on policy, this steady state distribution has to exist. And if all those things are true, then we can refer to the average reward independent of S naught or A naught. So now this expression is just like a single expression that only depends on the steady state distribution, the policy distribution, and the transition function of the problem, right? And so we've removed, so like for this to be true, like we've removed all reference to a starting state. Um, so those things have to be true. Now, in the book, they mention this thing about it being ergodic, and this is true. This probability must exist, but I mean, it's actually more than this, because this probability could exist. And I'll show you. So here, I'll just show you an example of this. So remember, we had this grid world problem. It's very simple. I have the option of adding some more complexity to it. But this grid world, like it starts here and there's a goal state here. And in this setup, like there's no wind or anything. All the moves are deterministic. So then, and here I've set it up so it's a continuing task. So you can enter the goal and then you get transported back to the start if you reach the goal, and you get a reward of 1 for reaching the goal. So because this is a continuing task, we can't solve this problem without having some discount rate, which is here, which the whole point of this is to solve these types of problems without a discount rate. But the way this grid world is set up under these conditions, this optimal solution where you just go straight to the goal doesn't depend on the discount rate. So like if I make the discount rate lower, this is going to stay the same. Like the values will change, but the policy will stay the same because it doesn't depend on it. And now, if you look at this solution, so this is going to produce a reward sequence that is like a repeating sequence, right? Where it's 0, 0, 0, and then eventually there's a reward of 1. So this does not meet the criteria we need for this. However, there is like the steady state distribution, I believe, does exist because there'll just be an equal amount of time spent in each of these states. But the problem is, if you were to ask, like, if you were to write this down the way it's defined, where you say, like, okay, what is the probability, like here, of being in state S? This long-term limit actually doesn't exist. So, like, according to this definition of the steady state distribution, this problem doesn't have a steady state distribution, right? Because what state you're in will actually depend on T. And it will also depend on the starting state, because like if you were to start out here, then you would have a different repeating sequence of states for each time step than if you were to start here. So one way you can see that this fails is if you look at this equation, this is also another part, this is a property of the steady state distribution. So if this exists, then you can write down a recursive relationship for the steady state distribution, where if you take all of the states, so like if you look at a given state and then you compute all of the probabilities of where you end up from that state, and you update the steady state distribution, then you will end up with the same distribution. So this is like kind of like a Bellman equation. Like this is a recursive equation, but it's actually these are for probabilities, not for values. But this equation is just saying, like, if this distribution exists and it's correct, then it should meet this criteria. But you could also iteratively compute this distribution. Like normally, if we want to know the on-policy distribution, like, well, I had it for chapter 9, but you could just take a policy and create a bunch of episodes, or take a bunch of steps in the environment and then start collecting the statistics of what states you're in. But in this case, let's say we have the whole transition function, we have this P, then we can actually compute this distribution like with this update rule. So, and I just added this here, some code that performs this update. So this, it just computes this sum. It takes the policy, it takes the probabilities, and then it loops through all the states. And it does the same kind of thing where there's some tolerance for error, there's a maximum number of iterations. So that's what's happening here. This is actually doing policy iteration on this grid world, because that way I actually like have a list of policies that we can look at for this. So like here's the random policy. So if you have the random, these are the value function for the random policy. And in the random policy, it appears doing this calculation converge, because I'm allowing it to go for more steps. So this actually did converge, like it's under the error tolerance. And this is what the state distribution is for this. Right. So it seems like the random policy with this problem meets the criteria here that we need to have a steady state distribution. Like there's not going to be any repeating sequences, like the policy is completely stochastic. There's an equal probability of making every move. And the starting state, not surprisingly, is the state with the highest probability because you're always transported back to this state. And then, state's far away. So the reason why this isn't like uniform is because if you end up randomly falling into the goal state, then you're gonna spend more time on this side of it. So now let's say this actually converges in one step of policy iteration. So this is already the optimal policy, right, where we just go straight across. And now you could see like the probabilities, the only probability now is to be, in this line. However, this didn't work. Like this process has failed, and you can see these values here. Like if I change the number of iterations this ran for, the values are going to shift around because this process isn't converging. So if you were to repeat this over and over, this is what happens. You just keep shifting what the probabilities are. Now, these values, right, like should, like this is like a poorly defined thing. I mean, we know that the agent will spend an equal amount of time in each of these states, but the problem is that it's a repeating sequence. So these probabilities, these expected values are not well defined in the limit. And this method of calculating it assumes that the limit exists, or that this limit exists. So, this is a case where this approach would fail, right? And now this is a problem where we don't actually need, like I said, the discount rate doesn't affect the solution. And one of the reasons for doing this is to get rid of the discount rate. But even in the problem where the discount rate doesn't affect the solution, this method will still fail just because this mu is not properly defined, or that it just doesn't exist. At least the way we're going to end up trying to optimize this and use these sort of new versions of the Bellman equations, these will all fail and they won't converge because of this problem with the probability relationship. Now, okay, so are there any questions about this or what the distribution?
If the initial distribution, so like we're assuming some initial distribution over states when we're calculating this, right? If that initial distribution over states had been uniform over all the states which are visited by the optimal policy, does it converge then? Like if you put in the right answer, it should be stationary, I think, right?
We can try it. Yeah, I wonder. So in this case, actually, it's going to be hard for me to enter that here because I have to know the index of these states. No, I guess I could. I could. Okay, I don't know if I want to try to do that now and see. I wonder though.
I mean, just thinking through it, it seems like it shouldn't, like it should, like you should have the stationarity condition or the sort of fixed point condition. Because like if you just think of it as like, okay, like sample a state uniformly from the sequence of states, right? That's like kind of the initial state. And then if you iterate one step of the probability of the transition under the policy, right? Then every state shifts module, other than the portal, right? One to the right, which means that the probability of the next state under the probability transition function they're all like 1 over n, where n is the number of states in the sequence. So it is still uniform, and the probability distribution has not changed.
Yeah. I wonder if there is some, yeah, it sounds like it should
But
work. I guess we could see it here. I guess the only issue could be maybe, yeah, so the policy in this case should have
is
zero
one,
probability of leaving this, right, this corridor.
right? So we can basically like remove the term, right? Like we can remove the sum over A and just like essentially have it be um the probability of transitioning to the sort of next state. Like so we kind of remove
It's gonna be
A.
one. And these are all gonna be one.
Well, so A, so the policy will evaluate to one for exactly one action, which is the optimal action.
Yeah, and then this
And it
probability.
essentially it selects the optimal action amongst all the probability distributions, right? And then we know, so this is the deterministic grid world, which means
Oh,
that if it
but
selects that exact action, then there's like a definite, like there's a definite
okay,
S
okay, wait,
prime.
yes. No, no, that is true. However, contained in this sum is also these other states, even though they have zero probability, um, if you're in one of these states, I mean, I guess that their contribution will be zero, but this is gonna sum over all of the states, even the ones that have zero probability of being visited. And this is correct. Like these zero values are should be zero, but I wonder if that impacts the conversions.
Oh, so yeah, okay, yeah, I see where it's confusing, right? Because the policy has to be a full map from states to
Yeah.
probability
So
distributions,
like
right?
well, this is showing what the policy is like up here.
Well,
So
that's
this
that's
value,
the argmax policy, but yeah,
yeah, but that's what's being what the steady state is being computed on here
right.
is this. I mean, this is showing all of the entire like here, like there's a uniform probability. Um, there's also the issue that at this state, the action is irrelevant. So here it's learned to take a random action because it always returns to the starting state. But there actually is an action taken here, but that probably wouldn't affect anything. But yeah, I wonder if, yeah, if you initialize everything correctly, so these zero values would be correct.
But it is like weighted. It's weighted by um sort of like S or like the distribution over S naught. Like I'm just wondering if like the initial if you had a policy that is optimal and the initial state distribution had zero probability assigned to any of the like states on the non-optimal trajectory.
Yeah. Which I mean, here it has found that part of the solution, right?
Well,
All
but
these,
I'm talking about the initial state distribution.
yeah. Hmm.
Right. So like I'm just saying that like I mean I guess yeah, this is kind of beside the
Sure.
point. So we can maybe
I
drop
just
this part.
wonder, okay, okay, but I would guess that it's not a maybe it's not a stable um optima where if there's a slight numerical error in something, it will eventually converge into this like repeating sequence of values. Yeah, because there's some in order for this process to converge, and even like for these things to converge, you have to have these like contraction properties of the map, or I mean, there's a lot of math behind it, and clearly this, if this was well behaved, it should converge with like any initialization. And
Well,
here,
not
it's
so
not.
not in so I mean there's like the initialization for the sake of iteration, but then there's the like
Mhm.
initial state distribution, which is like different.
Well, yeah,
So I mean
but that doesn't exist here. I mean, at least there is, yeah. I mean, the initial state distribution, I'm trying to
it,
calculate the steady state distribution.
right, but what I'm saying is that the initial state distribution, like depending on the choice of the initial state distribution. there may or may not be a steady state distribution. But I mean, I guess maybe that's obvious. But like
Um,
I think you can select an initial state distribution for this grid world that will give you a proper steady state distribution.
yeah, I so the way the probabilities are arranged, you sort of start here and end here and then go back. But I do wonder if it does does the distribution
Well,
exist and is independent of S naught, or does it actually depend on S naught?
I'm arguing it does depend on S naught, right? And I mean that's actually pretty straightforward, right? Because like this is like a shifting distribution, right? So there's a distribution of states for each t, and that's like a shifting distribution over all of these in the log like in the limit in some sense, right? Like for each t modulo, like yeah, for each so if there's like n, right, then for each of like the between 0 and t minus 1 or between 0 and n minus 1, there is a unique distribution that the stationary like it that it converges to. But that like the particular assignment to those t's probably depends on the initial state distribution, right? And like the example is like if the initial state distribution was like all on like the initial state 0, like or like the initial state distribution was concentrated on the start state or like the green state, which I thought I'm maybe I forgot what this problem is, but like I thought that was the case, right? But
Yeah,
if
well,
the
this, I mean, in the continuing problem, you could start anywhere, but you would get transported back here
well, yeah, I guess
if
that's where you get
you reach the goal.
transported back to. But if you said the distribution of S naught is, certainly the green state, right? Then the
Mhm.
probability distribution of ST for the optimal policy, the distribution over S1 is, certainly the state over, right? And so the
Yes,
sequence
although this
of
is when this updates, um, the update at a state accounts for all of the states that could transition into it.
well, so that's what, yeah,
Um,
and actually, so that's well, but that's the thing
so that would
is
be
that the
this,
states that could be right because but we're notice that we're
yeah,
assigning zero probability
yeah,
to
under the
all of the states
policy,
off,
yeah,
not
like
under the
it,
policy, under the initial distribution.
yeah. Actually, let
And
me
so
just
like
see
there's
here.
this so I mean I guess like there's this thing where like the initialization of the iteration that you're doing here has to like I mean ideally it feels like it has to be the initial state distribution, right? Because like if you just initialize that policy, like I feel like the initialization of the iteration can't be arbitrary. It does have to reflect the initialization of the state distribution or like the initial state distribution. But if you
Well,
think about it, sorry.
oh yeah, so well, you can't initialize it all as zero.
Yeah, so I mean, you could initialize it all to 0. And I like sort of my contention is that
No,
that
but
would
that would
represent,
fail.
or well, yeah, not all. So first of all, yeah, it does have to be a distribution, I think, right?
Yeah, and the way I've initialized it here,
Yeah.
I have initialized it as a distribution.
Like it could
Um,
technically be an unnormalized distribution, but that's beside the point.
yeah. Wait.
But I mean, but the thing that's the case here is like if um like basically what you're doing if you have like a deterministic initial state distribution, or like you have an initial mu which is deterministic, right? Or right like your initial iterate for mu is like focused on a particular state.
Yeah. Okay. Okay. So here, look, I will set mu for. So in this problem, for where are they? Maybe I erase that. So index 4 is the should be the start. So this will now redo it. Okay, now this is what it converged to.
Well, no, that's exactly my point, though. Is that like so the
Yeah, yeah.
distribution, the state distribution is now just like this cycling one sort of like one hot distribution.
Yes. Yeah. And that is yeah, now the what the real question is like forgetting this definition. So clearly, according to this definition, this is what this is computing actually, is this limit to infinity. And it's not converging. It's um
Right,
it's changing because this limit doesn't exist.
right, exactly. But then what I'm
So
saying is, sorry, go ahead.
yeah, yeah, which is why yeah, so perhaps if you initialize it with the correct distribution, it would remain
Can
the
you try
correct
that?
distribution. I can't, I, it
So
probably
wait, because you,
will.
so
Well,
yeah,
because I
I
have
mean,
to find what state indices are along this path, which I could get it.
so
It would just take a
oh,
little
I see.
longer.
I see what you're talking about. Okay, so it's like a kind of tricky to. Okay, yeah,
Yeah,
that
I mean,
makes
it's tricky for
sense.
me to do it like instantly, but
Okay,
yeah, yeah. So what is happening here is this process is actually correctly computing uh, this limit.
well,
And
it's computing the t or like it's computing the function of t, like the probability distribution over states for each t, but that probability distribution is not converging.
yeah, well, kind of. I mean, this isn't key. This is actually iteration. So really,
Okay,
each one of these represents an entire sweep through the state space, and then it ends up being the same value that you would get if you asked, what is this at time t equals whatever? So it ends up, yeah, computing this at a particular t, and that t sort of matches up with how many iterations we've done.
right,
But the
exactly.
goal of this is not like t isn't even in this equation, and there's no
Right,
reference to it, and that's exactly why like this will never converge,
right.
right? Because it's not well. Now, what I'm not sure about exactly is we have this definition. I think if you stick something in this and you just sample the state distribution over time and you compute the average like in this style where we just count like hits and then divide average, then I believe it does exist and is independent of t.
Well, yeah, so that's, I mean, they say that, don't they? That so like the thing is like 10.6 always exists, or well, not
Oh
all, I
yeah,
think exists under different conditions than 10.7, right?
sure. But in this case, like this is the reward value existing. Here we're talking about like the probabilities, but yeah, but the same thing happens where like so we could write a different definition of this, which was more like this, that was like counting time in a given state and then dividing it by the total time. And if we did that and we wrote something that computed that, like so it couldn't use this method to compute it. It would have to compute it like this, where we actually took averages. Then you would end up. So yeah, I believe that this distribution in this problem does exist. It exists under a different definition, though. Like this definition, this value, that this limit doesn't exist. Because
Right.
if you
Like,
start in some weird place and then you end up at the goal, and then you look at the states you're in the long run, like that sequence of repeating states is going, and you average the time spent in each state, the initial state is going to be irrelevant
right,
if you
right,
do that. Whereas it's not irrelevant if you make this leap where you get rid of the averaging and you just replace it with a time limit because the time limit doesn't exist. It only exists if we actually really compute the average here, where in this case of the reward, where we're dividing by the number of steps. Or if we're trying to do mu, instead of the expected value of r, it would be like the expected, like it would be this probability, right, of being in a state, and then these would be one because the sequence would actually like here, depending on what time step you're in, you have a definite probability of being in a state, and then we could actually average it through time with an H again, like we do here. But we're not going to actually try to solve these problems with this calculation. I mean, I guess, and we're going to rely on these Bellman equations. So we do need a problem where these processes actually converge like robustly. And I guess if this process converges when the probability is correct, that's fine. But then we already know the answer to begin with, and we don't need to do the calculation anyway.
Right, right,
So that's so like this isn't worth. This is sort of worthless for solving the problem if it needs to be
right,
initialized with a correct answer. But
right.
yeah,
But
I'll
yeah, I
take.
mean, yeah,
But I'll go. So what did I do? I had this. Okay, so if I go back to the random policy, we can see now we're back to something working where the initialization doesn't matter. We have this correct distribution, and maybe I might as well just leave this here because well, nah, I should go back because I want this to be more generic to work for more problems. So this, okay. So the other thing we had looked at was now I'm going to make the problem stochastic, but it's still tabular. So now I'm adding wind, and remember in this problem, so there's wind values in these later parts of the grid world, and it blows the agent up. So like if you try to move in a given direction, you will also move some number of steps up in the direction of the wind. I think there's some other place earlier where I showed the wind values somewhere, but whatever. It doesn't matter. The only thing that matters is that doing this does change the solution, or what is the optimal solution. And more importantly, it even changes, the optimal solution changes with the discount rate. So here I'm making the discount rate very close, arbitrarily close to 1. And we can see now that it appears that this converged correctly. So like now the policy is partially stochastic. I mean, there are states where there are, some randomness to the actions. This, you can make this gamma arbitrarily approach 1, and we end up with like, so the wind ends up sort of blowing the agent up and around, and this is the learned policy. And this seems to have, yeah, right, like this is actually converged in some finite number of steps. It's under the error limit. This is not changing. Okay, so that's good. Now let's say I change the gamma, so I'll make it like kind of low like this. So this still managed to converge, but we can see that the policy, the values, and the steady state distribution appears to be totally different. Here I'm, I have a lower discount rate, so future rewards are discounted more, and I guess it ends up like this also isn't the case where I've added a secondary goal here. Like the secondary goal, there's no other goal to reach except this one. So it's still, all the time is spent focusing on trying to reach this goal. But depending on your starting point, like the discount rate does affect what you aim to do. Like if the discount rate approaches 1, then you definitely want to move to the right at the start here, and this becomes like much more deterministic. As I make this lower, then suddenly like there's some equal chance of going down, and yeah, you end up spending more time in this state like directly above the goal. And I guess I'm trying to think of why I had previously done this with a secondary goal, and then it was much more straightforward why changing the discount rate affected the solution, because it was actually related to like the average reward and which end state is closer to the starting point, um, depending on what the reward is. But in this case, you can see even without two goals, just making this problem stochastic, now, changing this gamma affects the optimal solution. Yet this steady state distribution does exist. And one of the statements later in the chapter is that if we're trying to solve problems like this, and we can actually compute this average reward and it meets all these properties, then the solution should not depend on the discount rate. And we can just take the limit as gamma goes to 1. And there's definitely problems where that's not true, like where you end up with these repeating sequences. What I'm not sure in this case, because this seems to be a problem where there is a well-defined average reward and these distributions exist and you can find them and they don't depend on the initialization state. Yet the discount rate does still matter. And I think
Well, is it that the
part of
discount rate doesn't matter, or is it that the discount rate taken for the limit, like the limit of the discount rate going to 1 converges to the average reward case? Like
that is
the
true.
same.
Actually, no, that is true if the problem meets these conditions.
I see.
If
Okay.
you have a problem with like repeating sequences and limits not existing, then that's not true either. In fact, you can set up a problem like this where you can ask, what does the discount rate have to be for the optimal solution to match the optimal solution within the average reward setting?
Okay, I
So
see. So you can like
even
solve for
in that,
gammas.
you can solve for gamma, which is like picking the gamma, but it's completely problem dependent and initialization dependent, like because the discounted reward that we compute is really quite different from computing the average reward. I mean, yeah, you would think in the limit where gamma goes to 1, it seems like it should match, but I think that doesn't work when you start breaking these, like when these limits stop existing. But I don't know. I had some specific examples, but okay, I'll just skip forward to the part of the book where they make this statement. So the statement here is that if all those things exist, like we previously talked about, then we can change gamma, and changing gamma will affect like what the discounted sum is. But the policies, like every single policy, will be affected the same way by changing gamma. And the ranking of policies by average reward will not be affected by gamma. So this is defining like a new quantity, which is the average value, the average discounted value observed over the distribution, where now the value function is back to the original value function. And if we have a problem, like here, these steps are using the previous relationships that relied on those limits existing. But then if you do this derivation, you find that this quantity can be expressed in terms of, right, whatever the average reward is times some factor of gamma. But again, like this factor of gamma is independent of the policy pi. So if we're comparing different policies, they will still be ordered according to what their average reward is. Now, yeah, for this, so like if we look at this problem, now this is the policy where gamma is like point, like close to one, as close to one as I can get it here. And this is what the distribution looks like. I mean, part of the, this is also for a given policy. Um, I guess I should say here that I'm not like, what I have not done here is like taken a policy and adjusted gamma and seen like, because here it's actually optimizing the policy as part of the policy iteration. But the final statement here is that whatever's considered the best policy should just be the one with the highest average reward. And so like here is the policy where gamma is 0.99, and then I'll turn this down to like a lower value. And now like it is a different policy, unless the policy could be the same effectively as long as like what this policy is saying is that these two actions are equally good, right? But the policy that only takes the right action is still an optimal policy in this case. Like what we're free to choose. So I guess you have to pay attention and see if any of these actions actually like change. It's possible that what's changing here is only the inclusion. No, I believe it is changing, right? Because if I go down here, this is saying like the down action is never allowed. And that didn't one of these actually flip? So this, yeah, some of these flip from down to right. So I believe like the policy is meaningfully changing. But I can show you a case where it really does change here. So if I make this like have a reward and I make the discount rate like really low, now in this case, because I'm discounting future rewards a lot, and this goal, actually wait, I'll make this like lower. So yeah, so this goal has a lower reward than this one over here. But if you start from this state with this discount rate, the most favorable thing to do is to go to this goal. Now, if I make this 0.99, okay, wait, I have to actually make this a little worse. Or yeah, so now with this discount rate, starting from this, the favorable thing to do is to go for the goal with a higher reward because that future reward isn't being discounted enough to make this one look better. Now, if I turn this all the way down, now from here, it goes to this goal. And we're back to the same problem now where this distribution is not converging and it's going to change. And it now depends on the initial state. This, wait, if I made this 0.99 again. And now in this case, like the distribution appears to exist and have converged. But clearly in this problem, the way this is set up, the optimal policy depends on the discount rate. And if I look at this carefully, I believe like, yeah, this really has converged. I think, yeah, because I think, well, maybe I don't know. It's possible that it actually hasn't converged and it's just whatever tolerance I'm using. I mean, there is some oscillation in the values here. I guess we can see the error value if it's even, is it actually dropping? It, oh no, I think it has converged actually, because this is now, I've just allowed it to go for enough iterations where this is now no longer changing, right? This value was higher before, right? This is at like 200. Yeah, yeah. So I think it is converging. Yeah. So anyway, there's cases of this where like I understand what is the problem, like, right? This leap we made writing equation 10.7, like, is a common problem if you have a repeating sequence. However, in this problem where it seems like there isn't a repeating sequence, I'm not sure what the problem is. It may be that actually there are parts of this grid where you can get repeating sequences where there's like no wind. Like here, if you take these actions, the movement is deterministic. So I was showing extreme cases where the entire reward sequence is like some repeating sequence. But I think you can get the same types of failures if you have regions of the state space where that can happen. And yeah, even if it's not like a global problem, and I think it still violates this ergodic condition.
Well, so to be clear here, we observe the dependence on gamma because this is not an ergodic system because it can have this repeating like sequence of rewards. And it's probably because of like some like the sort of like fundamental period of the
Oh yeah, you know what? Yeah, you're right. The fact that there is a gamma I can set where this really clearly fails
yeah, yeah,
already
exactly,
means that
exactly.
yeah, even if I find a gamma where it seems like this should work, that doesn't matter because like this
Well,
property has to hold. Yeah, and actually, okay, I didn't say that earlier, but eventually when we actually go to find the optimal policy, this property has to hold for every policy, right? Because like if we
the
end up
this
iterating and we end up temporarily with a policy that where these like limits don't exist, then
oh
the
yeah.
process will fail. So yeah, I believe we can't have a problem, which means the environment has to be like either partially observable or like fundamentally stochastic everywhere in some way to prevent that from happening. And this concept is introduced in this section on approximation because in approximation, we have an infinite number of states. So another thing that can save you in this setting is like here, the problem is that we have a finite number of states. If we have an infinite number of states and we have these dynamics um, where we can't even like observe the exact state because we're mapping it to something else, this thing we're gonna well, no, I guess because this property should hold for the continuous state space as well. But I think whatever policy we define in the approximation problem, because the policy can't actually like depend exactly on the state, then it's going to inherently force, some stochastic behavior because yeah, and I wonder if you can see that even with the like in state aggregation or something. Because when you end up computing an action for one of these policies that we're going to be talking about, like in the mountain car problem, right? We're like here, like you can see in the tile coding, we've sort of like we have this blockiness to the state space. So when we're in a state, we have some action, but we don't like know exactly what state we're in. And actually, the things that prove these properties in the chapter are problems where we just have where we can't say anything about what state we're in, and we can just look at the reward sequence because that ends up um, in that case the only problem you run into is if you have a repeating reward sequence, um, which actually I believe would be the case. No, I mean it would never be the case in because the way the mountain car problem is defined, the initial position is sort of randomly chosen within a range. And you could define the mountain car problem where it always reset to the same exact position. And then it's possible because the problem is deterministic that you could have a policy that did produce an exact repeating sequence of rewards, and that may also fail.
Well, I don't think that the problem is like an exact repeating sequence, as it is like it's kind of hard, but I think that the problem is like some characteristic frequency of the MTP, right? So like it's not like there's going to be like some sort of like chain, like sort of like discontinuous change going from
Oh,
like
you
a
mean
initial state distribution of like a single value in the mountain car problem to like a small interval of values, right? Like it's not going to like suddenly break every like some sort of assumption.
yeah,
Um,
actually, no, I think you're right that the mountain car problem would also fail even in the approximation case, because if we look at this limit, it probably does oscillate with time.
well, so we're assuming like an extension of the mountain car that's like the same as the grid world where you're just like teleported.
Yeah, where it keeps
Yeah.
resetting to the start. You end up with the same problem where there's this time dependence.
Yeah, exactly. Which is like it's like the fundamental like time to solve. I mean, it's like the episodic length basically. It's like the sort of
Yeah. Well,
yeah,
even though in the it's going to be fuzzy, like the problem could be stochastic. We might not have an exact sense of what state we're in, but
right.
like you can see if this solves even in like some range of steps, then you are going to get a clear time dependence in the reward limit.
I mean, I feel like this is like a very intuitive thought, but this is like the difference between like it's kind of like the difference between like episodic games and like just like steady state games generally is like what sort of I don't know. I'm just like I'm thinking of
But we
Atari games where like the like steady state games are like I don't know asteroids or something where
but
you're
we
just
can
trying to like
always I understand, but like theoretically, we can always convert an episodic problem into a continuing one.
yeah through this, but that almost always turns it into a problem where you have like some sort of periodic like at least like for an optimal policy and probably for stochastic policies as well. You
Hmm.
probably have like some sort of fundamental characteristic frequency of the problem.
Yeah.
So like
And
we
that
like I mean
Oh yeah, and that's also, but if you have a problem like that, it also implies that like the discount rate has a significant meaning to the problem.
exactly
Like
yeah.
it actually affects the solution. Now, in the mountain car problem, we had done a reward of -1 per step without discounting in an episodic case. And that just encouraged, the problem to find the solution fastest. Which I mean, if we do the analog here, it would just be like the old solution where it just sort of went straight for the goal. Now, I showed a case where the discount rate. So what kind of surprised me, at least in this problem, is that I understand if you have like two different places that you can go, and there's a different distance to each one, then the discount rate really has an important meaning to the problem, and you're making a different statement about like what is valuable. And like I said, I have it written down somewhere, but if you set up a grid world like this that's not stochastic at all, and you can just go to one goal or the other, and one goal like has a reward of R1, this has a reward of R2, and this has a distance of D1 and D2, then for those particular values, you have to actually figure out the gamma that gives you the average reward answer, because the gamma limit in any direction, it doesn't like actually give you the correct answer if you care about the average reward. And if you take the limit as gamma goes to 1, you end up with an answer, but it's not necessarily the average reward answer. It's just like it's something else, which seems like it should be a fundamentally important answer, which is like, what is the reward for this problem when I don't care about discounting? But like weirdly, it does not map on to the average reward solution, which you would also think is some like fundamentally like sound approach to solving the problem. But that's with like two different goals that are in different places. The weirder thing is that if you make this problem stochastic like this, that even just making it stochastic makes the discount rate affect the policy and the distribution. And here we're seeing that if you really discount rewards, which means like over here, we're not looking, very far into the future, but I mean, it ends up favoring something where you spend way more time um, in this state because I guess even if you go back to the other solution, like once we're in this corner of the problem, we have a much more reliable path to the goal, or we're much more certain of reaching the goal. Again, it does seem weird. I mean, unless there's something wrong with how the solution is working. Oh, also, if if the steady state distribution changes, wait, and actually has this yeah, and this is actually even this is converged. If the steady state distribution changes, that does mean that it's a different policy, right? Because the policy should have the same policy should have the same steady state distribution. It could still be one of some equivalent policies, like in the case of equally favored actions. But it seems like in this case, like the policy is fundamentally changing.
Like as a function of the number of iterations. Like it's
Well, this is still no, this is showing the final converged optimal policy.
right. But so this is the steady state distribution of the converged optimal policy.
Yeah.
But the thing is like, so if you modify mu the 500 there, it's moving.
Well, no, it's actually converged after 185.
So just to be clear, this is a bound on the number of iterations.
Yeah, this is an upper bound. I only did this so that in the case where it's not converging, it will actually just always go to the upper bound. And then I can change the upper bound and it will shift the distribution. And you can see like these are not zero, these values here. There's like non-zero probability throughout here.
Okay.
But the policy itself is such that it's causing way more time to be spent in this like upper right corner. I mean, also in this band here, right here, like these now, like actually are zero probability. These are zero.
So we have like a converged steady state distribution.
Yeah, in both cases. Yeah, converged policy and converged steady state distribution. And the policy is different. I mean, if you have a discount rate closer to zero, you are much more risk averse in the like behavior because like you can't afford to, I mean, you have to put yourself in a position where some reward is like more certain in a shorter number of time steps.
Right.
And that's why like the policy is changing. Because like this is different from the case I showed before where I turned everything off and now this actually isn't converged, right? This is all at the max iterations and
Right.
it's,
It's
you know,
cyclic.
yeah, it's cyclic. But this is also the case, right, where like this is now not converging and not working. However, this problem actually is the average reward solution because it doesn't depend on gamma. And I guess another statement you can make is if you have a problem where you notice that the optimal policy doesn't depend on gamma, even if this whole thing fails, then you know that optimal policy is the highest average reward as well. Because it's like, I mean, it's one of the I mean, it's sort of like the backwards version of this, where like if the policy ordering doesn't depend on gamma, then we could replace it with like this average reward. Um, even though this doesn't actually exist, like in the way it's defined earlier, but it
Okay.
does exist just like this exists. Um, if you compute it in this way. But I guess, this problem also has this like periodic structure to it,
Well, so now
which,
I am confused because I thought that you like this problem like fundamentally should have some sort of like fundamental frequency to it. And but like now you're telling me, or well, so yeah, there's a steady state distribution. Can you set it back so that it has a steady state distribution that's converged? That was that
but
like
this
high
one,
gamma?
oh yeah, high gamma. Or,
Or I think maybe it was low gamma.
no, this is
The
converged.
one,
Oh yeah,
okay.
I can set it
Hmm.
low. I mean, both low and high in this case are converged.
Okay, I guess I'm confused by this because it seems like how do you have a steady state here if like yeah, I guess I don't I'm not sure I
Yeah, it's like
understand why you have
why would the policy change with a different discount rate?
well no, that's not my I'm wondering why the steady state distribution exists. Because like for
Well,
some reason
this is
I thought that
now,
this problem would always have a like my contention here on this problem was that it always would have or it would always lack a steady state distribution. Because like this problem is like fundamentally has some sort of like time characteristic to it.
mhm.
And that's why there would never be a steady state distribution unless the initial state distribution was identical to the optimal policy distribution, like I was saying earlier.
It is, hold on. I can change, we can see,
I guess I mean, it has something, must have something to do with the wind, right? I guess maybe I'm not
wait,
understanding.
I'm sorry. Yeah, there is stochastic wind. Okay, so I just set the tolerance to 0. It does seem to be converging. Oh wait, I'll set this higher. Yeah,
Can you just increment it? Like it doesn't,
mhm.
it's not doing this like cyclic thing.
No. So I like previously I had the tolerance set to like machine epsilon. So I just set it to actually 0. And now it says convergent 517 iterations. Yeah, I mean it has, I mean if it's 0, it means that on the previous update, like not even in fine decimal points, like none of the values changed.
I don't understand that at all.
Yeah, it is a little.
Yeah, I mean, so can you just like turn off the wind
Mhm.
or like yeah, I guess, but yeah, okay, turn off the wind. Now it does the oscillate, the
Oh
rotation
wait,
thing, basically.
I could do something else. So I'll put wind on without
But
stochastic wind. Now this has failed. Okay, so this is non-stochastic wind, and now it is this policy that wraps around, and we can now see, does this depend on the discount rate? No. So if the wind is not stochastic, then the optimal policy doesn't depend on the discount rate, and everything's deterministic.
and
Funnily
it's iterative.
enough, and this solution will match the average reward solution, yet all the conditions for doing the average reward test are not met because this distribution doesn't exist. But it doesn't matter because, so it's like we have the gamma independence even with all this failing, but
Right.
it's not for the same. Well, in this case, the gamma doesn't exist because we have this like non like this completely deterministic repeating sequence. If I make it so maybe I guess what we were saying before is that even if you have a periodic, you know, but I don't know, I would think in the long-term average, yeah, you would get these like peaks in time of different expected values, but maybe you
Yeah.
don't because even a
Because the
little bit of,
stochasticity like accumulates.
yeah.
Like a small bit of stochasticity is going to mean eventually you
Oh,
just
so
like
it does
spread out.
smear. It
Yeah, it
smears it
smears.
all. Yeah, but because you think like, let's say you do the mountain car problem and like it is stochastic, not because of
What
the approximation,
what
but
is the
like
stochasticity in the mountain car problem?
there isn't any.
So it's deterministic.
It's deterministic, but with the approximation, it's as if it's stochastic where we have an uncertain state that we're in.
Oh, okay.
Like
Yeah.
we
So it's
don't,
the approximation. Okay.
yeah, so the approximation grades it. And then let's say we have a policy where we always finish the problem like between 100 and 120 steps. And then you're trying to compute the expected value. So the mean step is 110. And then what you're saying is if you look at the expected values of reward at like 110, 220, 330, out to infinity, that those peaks will disappear, even
Right.
though even though you have this bounded like certain um range of possible episodes.
Right. As long as like every episode length. Well, no, I don't think you even need every episode length to be feasible. Like you just need like
No, I'm
the
just okay.
delta between the average episode length and the real episode length to be any arbitrary value. And then any expected like you can have any amount of skew or whatever. But the stochasticity allows the steady state distribution to form because like I don't know
Oh yeah,
the
so let's say you finish either in one step or like in 10 steps or 11 steps. Yeah, like the even that difference in the long term, it will smear out the probabilities across all 10 of those steps that are
right
like in the
exactly
period.
because yeah exactly because you could have like maybe or I mean I guess so yeah because even if you had like 50% chance of ending in 10 steps 50%
Yeah.
chance of ending in
Well,
11
even just
steps
like a 1% chance of the other outcome would still make the limit exist.
exactly
Yeah,
there's like
because which is why the approximation case, well, like we always
works
have some stochasticity because we don't know what state we're in.
right exactly
Well, not from P. We have it from pi.
yeah yeah exactly but
I guess, yeah, because like in the mountain car, it's a deterministic problem. So you should have all the same problems you have with the grid world. But every single pi that we pick, oh wait, actually the mountain car. So here, I'll show the beginning of the mountain car problem again. So this is the policy that only like moves in one direction, right? And it just oscillates back and forth. And the problem's deterministic. The actions never change. So I believe this whole thing should fail in this case as well, even with approximation, because right, like these are being computed on the actual problem, right? Not with approximation. This distribution, I mean, this distribution clearly doesn't exist because, right, we have a
yeah
periodic, um, yeah, this is periodic and it's going to stay that way. I mean, especially because this will never terminate anyway. So we're never going to like
Right.
reset the problem into. Now, if you turn this into a continuing problem where after like n steps you reset it, then maybe it, yeah, because the period of oscillation depends on the starting, on where you start in the trough. See how it's like shifting where the peaks are?
Yeah. Well, but like, does that? I feel like that doesn't make mu exist.
I think it I think it would, because then if these are shifting around these peaks and you smear it out over infinite time, you would then lose the ability to know what state you're in, even if you know the cutoff time.
Yeah. Okay. So
But
but that's just like spreading. It's sort of like you have like a random like
yeah,
I know this is
well,
wrong, but you have like some like random potential energy or something, and it's just like you have um like I don't know.
well, no,
I guess like yeah. Go ahead.
like in order to convert this into a well-behaved continuing problem, you probably do need that reset after a set number of steps, regardless, because without that reset, yeah, you lose the ability to have this distribution.
Well, so but no, you can have a continuing problem mountain car. Like why do you need the reset?
You don't need
Or
the
like you
reset,
need the
but you need
reset
it
to solve the problem
with average reward.
without correct. Yeah, I agree with you.
Yeah, because you need to introduce this, like you have to have something in the problem that breaks any kind of periodicity.
Right.
And you could
Which is
actually
either
have
randomness in the policy or yeah.
no, but you can't rely on randomness in the policy because the policy could be deterministic.
Right. Or so yeah,
Like,
randomness in the environment or some randomness. Yeah, I guess it has to be randomness in the environment, which you could like force through the reset.
because you could always start with a policy like this, where you're just like, only choosing one action.
Right. Right.
And then it's a major problem. Yeah, and I guess even if the periodicity is just slightly less than perfect, that is enough to make this work because it'll smear everything out, all the probabilities out
Right. Exactly.
in the long run. So that's sort of somewhat encouraging, which is, I guess, why when I make this stochastic, suddenly everything is okay. Um, well, weirdly, again, this is sort of a paradox because it makes everything okay with this, with this distribution existing, but it fails the property. It fails this property that the discount rate shouldn't affect the policy. So then it brings back the
Right.
question of what is going wrong in this derivation that is that is making this fail. Because mu existing is not failing now. And the reward sequence, I'm trying to think. I had written down a couple. Wait, let me see if my notes on this leads to any insight. So we need, okay, yeah. So like we need the average reward to exist, which usually it does. We need the long-term limit to exist and not depend. Oh, we might be. So clearly this distribution exists, right, and doesn't depend on S naught, right? Because in order for this to converge at all, it can't depend on S naught.
Right. Right.
That works. I wonder, is it possible that this depends on S naught, this limit? But if this limit exists and this distribution exists, that should be enough. We have the problem. I mean, I believe the problem in this case is ergodic from the stochasticity. Anyway, I thought I had this figured out in the case of like, well, of course, this fails when you have like a non-ergodic problem and you have these repeating sequences of rewards. In this case, we don't have a repeating sequence of rewards. We have a true steady state distribution that exists. However, yeah, there is still some problem with defining this. But actually, the average reward, yeah, so I guess, as I change the discount rate here, like this policy, as I make gamma approach 1, should have a higher average reward than this one, I believe. But I would have to actually compute that to verify it, because what's being shown here is the discounted value, which then depends on how many steps it took
Right.
to reach. But yeah, I guess we had gone over this. Yeah, I mean, there's something in this proof. There's some assumption in this proof that has to be violated in whatever's happening
Right.
here. And I'm not sure what it is. It may even be something so subtle, like it's not even mentioned in the book. Some other assumption.
Yeah.
But it's certainly the case that, yeah, the average reward exists. So I don't know. I'd have to think about it
Well, the
more.
average reward always, or I mean, I guess almost always exists, right?
Yeah. Well, no, yeah, that is true. But I mean, it has to exist and it has to be computable like this.
Right, right.
I mean, the only thing I can think of is that
I mean, can you just implement the differential, like differential Sarsa and see what happens?
differential source. Oh, you mean solve the grid world problem, this same exact problem, trying to use average reward
Yeah.
and see what happens? Yeah, I could try that more and see what happens. I can't imagine though it would. Well, no, I mean, yeah, it could be a different answer. Yeah, I mean that is something that I could do. Yeah. I mean, I guess after all, like the discussion of all that, these exercises may seem kind of simple, but well, actually, we didn't even look yet at the pseudocode for or these expressions. But the point is that if we can compute this and all these limits exist, then we can define a new discount rate, or sorry, a new um, return value, which is now the average. So instead of summing these up with gamma, we're summing these up and subtracting the average reward of the policy, which we're assuming we already know, right? So
Right,
this would basically like be zero or most of the time because like these rewards being added up, of course,
right,
like it depends on what state we're in. But then when we then compute the value function, instead of computing the expected value of the discounted return, we are now computing the difference between the expected sum of rewards from that state with whatever the average is. And then, certain states may have a higher value. But now we are no longer trying to compute, like in this case, the V star is not actually like this will not have the highest values necessarily, but what it will have is the highest average reward in here. And you can kind of think of the Bellman equation update we did before, which is like, let's say we have a policy and we have successfully computed what this R is. So we have it. And then we look at different states or different state action pairs. Like if we are able to select an action which has a higher differential value than whatever it was before. So then like this reward sequence is going to be mostly like the same as before, but we're going to have, some step of it where the value is higher. Then that like, well, here you can see like we're maximizing the action here across, something that should have, right, this higher, this is like an estimate of what G is. Then when we boost this up, then that new policy where we compute this will have a higher average reward than the one before it. And like this derivation isn't as thorough as it was when we looked at like deriving, value iteration or policy iteration, but it's because all of the math is like mostly the same, except all of the references to gamma have been replaced by this average reward. And then you just trust that, this iteration process that we're going to do in here for Sarsa is because it's not going to be increasing the value function, because the value function, right, is just, like the average across all the states is going to be a 0 for the value function, right? Some states are higher value, some are lower, but they average out to 0. The thing that we're actually trying to optimize here is make sure that the average reward is higher. But then, this differential Sarsa ends up looking the same as semi-gradient Sarsa from before with the update, right? So here the update was we have this U estimate, and the U was, R plus gamma times the action value at the next step. And here we have something that looks almost the same. The gamma's gone, and we have replaced it now with this subtraction of R bar, where R bar is our current estimate of what the average reward is. And this estimate has to be updated as well. And one way of updating it would be to just take all the rewards that we observe and average them together. But actually what's done here is not that, and it uses this delta. There's an exercise about that later on. And then, right, this is the expression for doing semi-gradient Sarsa. There's an exercise here about give the pseudocode for differential semi-gradient Q-learning. I mean, it's pretty straightforward. Like in Sarsa, we choose A prime, and then we use that A prime on the future step for the value. Whereas in the case of Q-learning, just like we did before, we look at all the possible actions at the next state and choose the maximum one. I mean, Q-learning also relied upon, like, remember, these value functions actually like depend on the steady state distribution, like we had said before. And here, like where with Q-learning, it was pretty well behaved. In this case, now like the R bar that we're computing and updating is actually based on the behavior policy, which is not necessarily the policy that Q-learning is trying to optimize. So this is a little bit fudged in the math where you're just like, well, we'll use the R bar anyway. And also, if you add a constant value to this, it doesn't affect the relative differential values. So maybe it doesn't matter. But the important thing is like, once you have these equations and you update it, you do also have to worry about the R bar update. And that's what's done in here. I mean, that's the subject of this exercise too. And then the rest of the chapter goes through some other, I mean, the math of the examples is somewhat, it's a little bit more explicit in dealing with the cases we talked about here, the failure cases. I also wanted to go over one of these earlier examples from chapter 3 that had the same thing where the policy did depend on gamma. But again, the reason why that fails is the more straightforward reason that we already talked about, where wherever where the limit doesn't exist, right? Where this limit doesn't exist, and that's the problem.
Right.
But I think it's probably already been a lot. So I don't know. What do you think? We should maybe finish it at the next meeting,
That sounds reasonable.
rest of the
Yeah.
chapter, because I think yeah, we had sort of a longer discussion about this example, and I still don't know. I will try for the next time to have a more clear answer about why this seems to meet the criteria for the average reward setting, and yet the answer does depend on gamma. And
Yeah.
I do have notes. Actually, I could look. Hold on. I think I had written down in this tablet. I had derived something about the discount rate. Wait, let me see if I can just share this quickly, if this clarifies anything. Sorry, just that's it. Okay, okay. Uh, so wait, I had written this down here where I imagine that we have starting state, two goals. I guess I have to zoom this out a bit. So whatever goal you go to, you always return here. And then this was, so because this is a grid, you can see how many steps there are to get to each state. So
Right.
to get to state A, it's 6 steps. And to get to state B is only 3 steps. And then, or wait, no, I end up changing this. So yeah, the rewarded A is 1. N is the difference in steps to reach the farther goal. Then as long as gamma to the N is greater than R, where R is the ratio of the closer reward to the farther reward, that is the condition at which the policy changes. And then you can also treat it as a continuing problem. Let me see here. So here I was trying to connect it to the average reward, where now you have, right, this sum where instead of this gamma relationship, we care about whatever R is divided by the number of steps. So I haven't looked at this in a little while, which is why I'm trying to see if it makes sense. But I believe what I was computing here is the value of gamma where the solution is equivalent to the average reward one. Um, and I think it is this expression. So I think this is the value of gamma where NA and NB is the number of steps from the starting point to each goal. And wait, it doesn't depend on R. R is the reward ratio between the two. Well, I have to look at this again and see. Maybe someone else reading this can understand what the. If I found an expression that doesn't depend on R, I think what is the significance of that? Oh no, no, that does make sense. Why it doesn't depend on Why it doesn't depend on R? Because I'm trying to find a condition on gamma where only the average reward matters. And it does depend on the relative number of steps. well, I don't know. We can look at this again more later, but yeah, I was trying to form that the connection between yeah, the discount rate and the average reward setting. But anyway, clearly like this problem, the way it's set up, does not work with the average reward setting because this definitely has these repeating sequences of rewards, and the solution absolutely does depend on gamma. Yeah, but yeah, the
Yeah.
other case not so clear cut. Okay, well, thanks for coming, everyone. Yeah, we'll try to finish chapter 10 next time.